In this video, we talk about the method of hypothesis testing if I have two different samples. So the screen shows the samples that were collected from two different river basins in Ohio. One gives a mean of 0.035 with a standard deviation of 1.046. The other one gives a mean IBI of 0.34 with a standard deviation of 0.96. And so the question is, what is the does it appear that the two locations are the same or have the same mean IBI? This is a different type of hypothesis testing problem than we've seen in the past. Before, when we had one single sample, and the question was the mean of that sample consistent with some previously known population mean? This is a different example, which, truth be told, comes more often in real life, where we have two different samples, and the question is to compare these two different samples as opposed to comparing one sample to some hypothesized mean. So the parameter in question this time is actually going to be the difference between the two means. The first mean minus the second mean, and the null hypothesis will be that the difference is equal to 0. The alternative hypothesis also concerns the two different means. And this time I don't have any expert knowledge about fish populations in Ohio river basins, and so I will have the very modest alternative hypothesis that the difference in the two means is not equal to 0. Okay, we're going to have a z-test for this because I have two large samples, and as always the z-test will be the observed difference minus the expected difference divided by the standard error for the difference. The observed difference will be just simply the difference between the two means, 0.035 minus 0.34. That's the observed difference between the two means. The expected difference will be 0 because that is the null hypothesis, that they're the same. If for some reason I had some other number besides 0 here, then that other number would appear right here. Then we divide by the standard error. Now the standard error, the way we compute this is going to be different for two sample problems than one sample problems. And the formula goes that the standard error for the difference is equal to the square root of the first standard deviation squared divided by the sample size plus the second standard deviation squared divided by its sample size. Okay, now before I compute this, let's make a couple modifications here. Suppose for the sake of argument that I were to take this second term out. Then what's left would be, if I take the square root, it'd be 1.046 divided by the square root of 53. And that would be the standard error that I'd have from one sample. Okay, so let me put the second term back in. Okay, now suppose that I were to take this term out. Then what would be left would be what I had before concerning the standard error for the second sample. Okay, so putting those two things together gives me kind of a Pythagorean combination of the two samples. And this will be larger than either of those individual standard errors by themselves because I'm taking both of them into account. Okay, so let's do the calculation. And to do that, we'll use the TI calculator. So I have square root of 1.046 squared divided by 53 plus 0.96 squared divided by 51. And so I get the standard error of 0.1968 approximately. And so we now calculate the value of z. So that'll be equal to 0.035 minus 0.34 divided by the standard error that we just got, which gives us negative 1.5501. Okay, so that's our z value. And I should have wrote that down here. 0.1968 was the standard error. All right, now we have to decide whether or not to retain or reject the null hypothesis. There are two ways that this can be done. First, let me use the p-value method. So for the p-value method, the z value we got was negative 1.15501. And for the p-value method, for this one, I would find the area in both tails. So I need the combined area of the double shaded region that we see in the screen. Okay, so to do that, we use on the calculator the normal CDF command. And I'll take the area from negative infinity, negative 10 to the 99, to the answer that we just got. Now, if I were to hit enter, that would be the area in the left tail. I want the area in both tails, so I need to take that number and multiply it by 2. So the p-value that I get is 0.1211. Okay, so that is the p-value. That is bigger than my default value of alpha, which is 5%. And so my decision would be to retain the null hypothesis. The second thing that I could do, let me just clear off a little space over here. The second thing that I could do is to find the critical value. That is a logically equivalent way of proceeding. And to find the critical value, I would need to find the mark so that the combined area under the bell curve is 5%. So I'd have 2.5% in the left tail and also 2.5% in the right tail. And so that can be obtained by finding the Invnorm command. If I do Invnorm of 0.975, that would return the positive one, 1.96 approximately. And so the other side would be negative 1.96. The value that I had was negative 1.55, which falls here. And so that falls in the region where I retain the null hypothesis. So there are two ways I can proceed. I can say that this number here is greater than alpha, my default value of 5%, and so I retain the null hypothesis. Or I can see that the negative 1.5501 figure falls here, close enough to 0 where I decide to retain the null hypothesis. So in conclusion, I'll just simply type out my decision. We retain, let me get it a little bit bigger. We retain the null hypothesis. There is not enough reason to think that the mean IBI levels are different in these two different river basins. So the procedure of hypothesis testing is very similar. I have a new way of computing the standard error that is the primary difference in the way that we proceed for a large sample two-sample test. I should also point out that it is possible to do the calculation that we just did using technology. So let me show this on the TI calculator. We will go to Stat, Tests, and the one that I just did was a two-sample z-test. And I will be inputting the summary statistics as opposed to the data. If I were using the data, I would input the data themselves into lists L1 and L2. So going to stats. Okay, the first standard deviation was 1.046. The second standard deviation was 0.96. The first average was 0.035. And the first sample size was 53. The second average was 0.34. The second sample size was 51. And in this case, the form of my alternative hypothesis is that the two means are different, so I have a not equals. Okay, and so let's see what happens when I hit enter. Well, I get a z-value of negative 1.55 as before. My p-value is negative 1.211, and we have the summary statistics down here. So from this raw data, then I would make the decision whether to retain or reject the null hypothesis. You'll notice that the TI-83 does not return the critical values. It simply returns only the value of the test statistic, and also the p-value that goes along with the test. Finally, to continue this example, we're going to find the power of the two-tailed test if alpha is equal to 0.05, and we assume that the hypothesized difference between the two means is 0.25. So for this one, we proceed with the formula that we have on the screen that we presented in class. The derivation of this is very similar to looking to the formula for a one-sample test. The only difference really is that we have a difference of means here, or a difference of, the delta prime is the difference between the two means, and also the way that we compute the standard error in the bottom is a little bit different than what we had before. But otherwise, this has very much the same form as the one sample way of computing beta. So let's go ahead and do this. Once again, we have that the value of sigma is equal to square root of sigma 1 squared over n sub 1 plus sigma 2 squared over n sub 2. So we will use the values that we had before, where we found that the value of the standard error was equal to 0.196759. In our case, alpha is equal to 0.05, so my z sub alpha over 2 is going to be the mark, where 0.025 is the area to the right. So let me draw the picture again. Alpha is equal to 0.05, and so I need the total shaded area to be equal to 0.05. So the area to the far right here is 0.025, and we found this mark before to be 1.95996 using the Invnorm command for 0.975. It's very important in the formulas here that the z here is a positive number, so that the negative z sub alpha over here is a negative number. Okay, so this formula here, let's work out what the entries are here in the parentheses. So 1.95996 minus delta prime minus delta sub 0 is 0.25 divided by the standard error, which was 0.196759. So that worked out to be 0.68937. So let me write that over here. This is 0.68937. The other one is going to look very similar, except it'll be negative 1.95996 minus 0.25 divided by 0.196759. So very much the same as what I typed before, except I have a negative in front of the value of z. So this is negative 3. Negative 3.23054. So let me write that over here. Okay, so the value of beta is going to be phi of this number minus phi of that number. That's a fancy way of saying find the area under the normal curve between those two marks. So the value of beta, if I draw the picture under the different colored bell curve corresponding to the alternative hypothesis, we will have some area between 0.689 and negative 3, and whatever that shaded area is, that is going to be the value of beta. And so let's do that calculation, and for that we'll just simply use normal CDF between those two numbers. So normal CDF between the left endpoint will be the one I just got, and the right endpoint will be the top one, 0.68937 to 5 places. And so that gives me a value of beta of about 0.7541. And so that would be the probability of making that would be the probability of beta. I'm sorry. The question is to find the power of the test. So the power of the test will be 1 minus beta. So 1 minus the answer we just got is 0.2459. And so the power will be 1 minus beta. So 0.2459. So for this particular choice of the alternative hypothesis, the power is less than 25%.